Okay, so let's kind of first talk about the problem in a big sense. The problem that this paper is trying to solve. In their kind of setup, they assume that they have this replicated data store, a replicated state machine kind of situation, where every single node, every single replica has exactly the same copy of data, right? So, and they have these clients that submit transactions to this store, and essentially the transaction is replicated, and then it's being executed independently on every single replica of this replicated state machine database. So this paper doesn't consider sharded systems where maybe like partition A exists on some subset of machines, partition B exists on a different subset of machines, and you do the transactions across shards. So that's not what they're trying to solve here. Moreover, they're not trying to solve the distributed part of the transaction itself as much, right? So they already assume that you have this replicated state machine that copies the data, and we just need to make sure that all the nodes execute the transactions, right? And essentially have the same state. So here I show this little example. We have this Paxos box. We have one node as the leader. It has these transactions 1, 2, 3, 4, which have been replicated to the replicas, and all nice and peachy. And the client can submit more transactions to the system. Let's say transaction 5 and 6, and they will get to the leader. The leader will replicate them, and the database needs to execute them essentially in the same order, right? So, and it's pretty easy to run these transactions actually in this replicated state machine, right? We can run them one at a time because we already have this order established by the Paxos leader or raft leader. So we have the order, we have this log, we can run these transactions one at a time and arrive at identical states on every single node or every single replica of the database. So, problem is pretty simple. Like we have this naive solution, but it has a few problems. The problem number one is, of course, the fact that we need to sequentially process these transactions one at a time, right? So if we have transaction 1, then we have to finish transaction 1. Each node needs to finish transaction 1. The node finishes transaction 1 before it can start transaction 2, right? So these nodes, when they have replicated all these transactions, they kind of run at their own pace, but they run this sequentially. So maybe like single thread, single core kind of setup. So this is obviously slow if we have a lot of transactions, and ideally we want to take advantage of a multi-core CPUs where we can run multiple processing threads and hopefully run multiple transactions in parallel and process this batch or this log of transactions a lot quicker. So the second problem is the slow transactions, right? So if we have one transaction that is slow, like in my case, this is transaction 2, maybe it's very large transaction, it has a lot of things that it needs to compute. This will delay the processing of the transaction 3 and transaction 4, right? So this kind of slow transactions, they can manifest themselves in the tail latency of the system. So again, if you have multiple processing units, if you can parallelize the transaction execution at your node, you can somewhat mitigate this issue as well, because you may have additional processing unit that can maybe take care of transaction 3. That's the problem with this naive approach to running these transactions in this replicated state machine kind of systems. So naturally, as I said, we want to avoid this sequential bottleneck, right? What if we don't run these transactions sequentially? Like, can we actually do it, right? So we have ordered these transactions for a reason, right? So they've been assigned an order for a reason. Can we run them in parallel? Can we avoid this sequential execution? And in a sense, we can, right? We need to exploit the the independence of some transactions, right? So if we have transactions that are independent from each other, then it doesn't really matter when we execute them in relation to each other, right? Because they're attaching the same variables, the same state of the state machine. So if you have these two independent transactions, you can try to run them in parallel. So for example, in here I have transactions 1, transactions 2, 3, and 4. Transaction 1 reads keys A and B, writes keys X and Y. Transaction 2 reads keys C and D and writes key Z, right? So there is no overlap in what data these transactions need. So, you know, we can try to run them, we can run them in parallel, right? Because it doesn't matter if one is actually executed before another because they're not dependent. Now, in my example here, of course, transaction 3 writes variable Y, which is the same variable that transaction 1 has written. So, you know, there is a dependency here, and even if we had more processing units, transaction 3 has to wait until transaction Y has executed. So that's kind of the gist of how the systems like Calvin and the system that we're going to be talking today try to run these transactions in parallel. Well, of course, in my toy example, it was kind of easy to see and infer this dependence of transactions, right? But in real life, it may be a little bit more difficult. But nevertheless, we still use this idea of read and write sets, right? So like in my example, I had a transaction reading some variables and writing some variables. So that gives you the read set of transaction and the write set of a transaction. And you know, obviously, as in my example, if the read-write sets do not overlap between the two transactions, they're independent. So their relative order that doesn't really matter at this point. So as the paper states, figuring out these read and write sets is not always easy, right? So if you have these trivial transactions like I had in the example that pretty much said read this and write this and that, and that's it, and you know, we have this explicit read and write sets. But if we make things a little bit more complicated, it becomes not as trivial. The two kind of scenarios that the paper outlines is the scenario number 1 is when we have the read and write sets of a transaction depend on some input to a transaction. So as an example, we can assume this transaction that has some input I, and let's say if I is 10, then we write X equals 5. So we write 5 to the variable X. And if well, else, then we write a different variable, right? So we write 7 to variable Y. So this transaction only depends on the input given to a transaction. So it may be something in the code, right? Something that the client that runs the transaction, it knows this I somehow, and it uses this I to determine whether it's going to be X5 or Y7. So this is a more trivial example, but you know, still depends on some input that we somehow need to be able to understand to determine the read and write sets. The second case that they have outlined is when a transaction write set depends on the values that the transaction has read in its read set. Right, so maybe the transaction goes as follows. You know, we read X. If X is 10, then write Z equal to 5. Otherwise, write Y equal to 7. Right. So the write part here, like, it seems very similar to the previous example where the transaction depends on the input. But here, you know, we have to read stuff ahead of time. Right. So it's not given to us before we run the transaction. So in example 1, I was given before we actually start the transaction. In example 2, this X, we have to acquire it from the data state. So these are the two challenges with this read-write sets. And now we can go into how the paper tries to address these challenges. So the authors call their system a prognosticator. I have a feeling this is because it tries to prognose, get a prognosis of some sort on what read and write sets are going to be needed in a transaction, right? And this system proposes using symbolic execution to find this read and write sets of a transaction. In doing so, it addresses the first challenge of figuring out the read-write sets of transactions that depend on the transaction input only, right? So this first example, this symbolic execution solves pretty neatly. The second challenge, when we have a transaction's write set depending on the values the transaction has read, that's not as peachy here. There are some issues, but supposedly the system can still narrow down the scope of what is called reconnaissance transactions or reconnaissance reads. And they also claim that they do them faster than systems like Calvin. Which I'm not entirely sure that's the benefit of the actual system. It's more of an implementation here. So yeah, this second challenge, the dependence of a transaction on a read of the transaction itself hasn't been solved fully with this system. Let's talk about the symbolic execution a little bit. So this is the example that they have in the paper on some code that they can run the symbolic execution, they can run the SE analysis and try to figure out. Essentially what they try to figure out, they try to run this code without the variables, right? So you can think of a symbolic execution as trying to traverse the code without actually playing, like substituting the actual values, the inputs. The benefit here is that they try to construct all possible branches of the code, right? So all possible executions of this particular code that, of course, may depend on some input values, but if you can construct these all possible executions, then when you have the input value, you can pretty much plug it in, solve the constraints, and get the proper results. So anyway, the code here, sample code, is just a handful of lines. On line 2, they have X as an input. So they say, okay, in this case, the input is just going to be alpha. So we assign alpha to X, and that's pretty much this symbolic execution step. Line 3 does some operation, right? So it says we're going to take X and add 1 to it to arrive to Z. So X in this case has been assigned alpha, so Z is going to be alpha plus 1, where 1 is this constant that just happens to be in the code. Line 4 is where the difficulties and challenges of the symbolic execution come, and that's branching, right? So here we have this conditional statement, and depending on this conditional statement, the value of Z is going to be different, right? So they record the branching as this path constraint 5. So, the way I guess I can try to imagine this in a high level is they unwrap this if loops and if statements and for loops and so on, and create these path constraints to show under what conditions you take which branch and what is going to be the symbolic result of this branch, right? So if we take the branch where X is greater than 10, where X have been assigned alpha, then we go into line 5 and we change the Z, and Z is going to be alpha plus 10, right? So it was alpha plus 9, but then we added another alpha plus 1, and we added 9, another constant. So the final result of this symbolic execution here of this branch is Z is alpha plus 10 with this path constraint. And similarly, we have this else statement, with a different path constraint. So yeah, I'm not going to go into like a lot more details. They talk about quite a lot about the symbolic execution and optimizations they do with their like profiling tool. But the basic idea is that they take this symbolic execution, they reconstruct this symbolic results of the query, right? Of the transaction, and they call this a profile. And this profile will have all the branches that a transaction can possibly take, depending on the transaction inputs or depending on the values it has read from the state. And they use this profile to reconstruct this read and write sets. Okay, so how does Prognosticator actually run transactions? Well, to start with, it runs the transactions in batches, and this is very important. Like the entire protocol will not work without a batch system. And it distinguishes 3 types of transactions. So there are read-only transactions, which don't modify the state of the system. There are independent transactions, and these independent transactions, they solve this problem number 1, when the transaction only depends on the transaction input, but it doesn't have this self-dependency. It doesn't depend on what it has to read from the store, right? So this transaction solves this problem number 1, right? The transaction only depends on the input of the transaction itself. And dependent transactions are the problem number 2, when the transactions write set actually depends on what values have been read in this transaction. So yeah, let's look at the example that I have here. So I have 8 transactions, and in blue I have I've shown transactions that are independent transactions. They don't have any dependency on the read set, on the read values. But this transaction, for example, here reads A and B and writes some value X, right? And X doesn't depend on A and B. Like we always know it's going to write X. Like the value of X may depend on A and B, but not whether we are going to write X or not. So we always know that here we're going to write X. Transaction 2, in this case, it's a read-only transaction. Transaction 3, it's a dependent transaction where we, in this case, read some key E, and based on this key, we'll either write X or Y, right? And there are a couple more transactions like this. So the batching is very important, and it allows the prognosticator system to take a few really important shortcuts, right? So if we run all the transactions in the batches, then we can actually start reordering some of them within the batch without impacting linearizability, right? Or whatever the consistency guarantee that is provided by the system. But given that this is a taxi system, I would expect this to be like strictly serializable system of some sort. So they can start reordering it, and the first type of operations that they will do are read-only transactions, and they do them because they don't modify any state. They only depend on the existing state of the system. So if the previous batch have finished, now we can run all of these read-only transactions on this on the snapshot of the state from the previous batch. Without worrying that anything will change in the system, right? So we can easily parallelize this read-only transactions from this single snapshot, which is the result of the previous batch. The paper goes into a little bit more details in terms of how they parallelize read-only transactions. They do it slightly different than the approach that they take for the independent and dependent transactions, but the basic idea is here. You take a snapshot, assign the read-only transactions to multiple workers, and they can do it independently because like they don't modify the state, so they cannot mess anything up for the other transactions. So yeah, with the read-only transactions taken care, and now we have what we have left are dependent transactions and independent transactions. And here again, Prognosticator does some reordering, and it actually tries to run the dependent transactions first. It tries to run all the dependent transactions before the independent transactions. And to run these dependent transactions, of course, it needs to figure out what is the right set of these transactions, right? It can try to run them sequentially, but again, that's not the purpose here. We want to try to run them in parallel, so we need to figure out whether they have dependency or not, right? So to figure out the right set, they need to perform the read. So this is where this is when the reconnaissance read comes to play. So transaction 3 and transaction 7, they get reordered in this batch to execute before all these independent transactions. They perform the reconnaissance read of E for transaction 3 to try to figure out whether we're going to write X or Y. And X and Y are keys, right? So these are not values, but we're going to write key X or key Y. And based on this value that we read from key E, in my example, I would say that the right set is going to be X, and I put this little asterisk just to signify that this is kind of tentative, right? So that's not super set in stone because it's a reconnaissance phase and something else may happen as the transaction started to run. But the same thing happens with the transaction 7, right? So it tries to figure out its tentative right set. So in this case, I say, okay, let it be T. And for the transactions that are independent transactions, we don't need to do any of this reconnaissance. We just leave them in the batch in whatever the order, preserving the original order from the Paxos leader. Obviously, we have reordered them quite significantly here. But the client is still waiting, so we're not really violating any kind of linear usability rules and stuff like that. And yeah, so okay, yeah, here I reiterate what I just said. And the way the system Prognosticator runs these transactions is by using a log table, which is not a very, I wouldn't say that this is like a state-of-the-art thing to think of. Let's use logs. But their log table is really like not a single log. It's more of a collection of queues for each key in all of the transactions in a batch. Right, so if we go back to this example that I had, we already done this, the read-only transactions. We have dependent transactions, independent transactions, and we can construct this a log table, and for each key, we have the queue of transactions. So key A first appears in transaction 7. So we put the transaction 7 as the first position in this queue. Transaction 1 reads key A, but in this case, in this batch, we have ordered this transaction 1 after transaction 7 after the reordering. So transaction 1 goes after in this queue for the key A. And we repeat this for all of the keys that happen in the batch. So we end up with this table. So yeah, and Prognosticator, when it runs the transactions, it will only look at the transactions that are at the first position in the queue, right? So it's this head of the queue, and it will run the transaction when all of its components are at the head of the queue. So if we look at transaction 3, it attaches two keys, E and X, and they're both at the head of the queues in their specific keys, so we can run the transaction 3. The same happens with transaction 7. It does A and T. It's at the head of the queue, so we can run the transaction 7. So in this example, I kind of set it up so that these transactions don't conflict and they can just proceed as normal and get executed. If there is a conflict, if there is a dependency, So when it actually runs the transactions, it does the read phase again, right? So before we only did this reconnaissance read, so now it does the actual read of the values, and it compares whether we still need to write to the same keys, right? So if for some reason these transactions had a dependency and some value has changed, the transaction that comes after the value that has changed, that it has read in the reconnaissance phase, it will abort. So in my example, I don't have this abort, but it may happen if there is a dependency. And when the transaction is aborted, essentially it's being placed in this special like abort transaction list, which is then going to be used to reconstruct, create a new batch, essentially. So once the transactions 3 and 7 are gone, we update our log table. At this point, transaction 1 can execute because all of its keys are at the head of their queues. Transaction 4 can execute. And transaction 6 still cannot run until transaction 4 done. So we wait here. We don't touch this, and eventually we'll execute transaction 6 and then transaction 8 after that. So that's kind of the gist of it. I'm not sure this is a super innovative approach to actually running the transactions. And the only reason why it works is because of this batching, and because the order doesn't really matter that much, right? So the order that was prescribed by the Paxos leader, by this replicated state machine, it doesn't matter. Like honestly, you can reorder it however you want in a batch, as long as you do it deterministically at every single node, right? So if every single node can compute the new order of the transactions, then we can run this batch in this identical way, and that will be fine entirely. So in a sense, the order that was prescribed by the Paxos leader, by the replicated state machine, doesn't really matter that much. And I'll conclude with like a very brief mention of evaluation. They compared against Calvin and this system called Node, and they show that they do have a lot more throughput. Here I put the TPCC benchmark, so a lot better throughput. At least when there are a lot of warehouses, maybe not so well when it's just one warehouse, but can get a substantial improvement apparently. And this figure on the right shows the abort rate of the transactions. So naturally, they want to show that it aborts the transactions less frequently, and that they claim that's because of the reconnaissance phase that they run. They claim that Calvin runs it at the client side, so there is a lot more delay in the reconnaissance, and they run the reconnaissance after this symbolic execution only if it needs to happen, only if there is this dependency on the read set, and they run it relatively, like they can read directly from the store on the node, so there is no like network delays, and because they run the deterministic transactions first, it means that none of the independent transactions can interfere with the deterministic transactions and like screw up the reconnaissance reads. So there is a fewer chance that reconnaissance reads are going to get invalidated, because the only way they can get invalidated is because of the dependency on other dependent transactions. Okay, that's all I have